Hey everyone, welcome back to another video. So today we'll be looking at question 11, which is actually a requested question from one of you. It's from May-June 2025, paper 44. So without further ado, let's look at question 11 now. This is about a nuclear reaction. So let's look at it. The deuterium nucleus has a mass defect of 0.002388 U. The helium-4 nucleus has a mass defect of 0.030377 U. Helium-4 is formed from deuterium in a nuclear reaction that can be represented by the equation here. Okay. So, first one, A Roman 1. State the name of this type of nuclear reaction. So, as you can see, this is actually nuclear fusion. Three of the deuterium nucleus come together and form a more stable nucleus, which is helium. Instead of saying come together, I would say fuse together. Three of these deuterium nucleus fuse together to form a more stable nucleus, which is the helium-4 nucleus. I know in your marking scheme, they actually bracketed this word nuclear. So in Cambridge marking scheme, if they bracket a word, means it's not really necessary, as in it's not needed to score this one full mark. Because probably in this year 2025, many of them did not write the word nuclear, just wrote the word fusion. But I would suggest you just write the full form, okay? It doesn't take an hour to write. Just write nuclear fusion. Because you never know when they will say that, oh, the word nuclear is necessary. So, why risk it, right? Might as well just write nuclear fusion. Okay, now moving on to Roman 2. Show that the energy released when one nucleus of helium-4 is formed from deuterium is 3.47 times 10 to the power of negative 12. Okay, so they want to know that the energy released when one nucleus of helium-4 is formed from deuterium. Okay, so let's look at the information given. So they gave us mass defect, right? They say deuterium nucleus has a mass defect. So before even we begin, what is the meaning of mass defect? So mass defect, okay, let me show you an example. Just draw a bit. So this is a nucleus. Inside the nucleus you have a few protons and you have some, let me use another color, you have some neutrons inside, okay? Then what happens is, now let's say I want to break this nucleus apart. I'm going to break this nucleus apart into its individual nucleons. So that means all the proton is now separated and the neutrons are all separated because I break this nucleus to its individual nucleons. So if now I'm going to take the mass, let's say the mass of this nucleus is A, okay, and the mass of this individual nucleons is B. I take A minus B, this value is actually what we call your mass defect. Yeah. So that's why they call it defect. So this is the original mass. Okay, this is the original mass. So now what I'm going to do is, I'm going to take this, I'm going to break it to its individual nucleons. So it'll become like this. So if I take the mass of the original nucleus and the individual nucleons, I subtract it, the value is what we call as mass defect. You can also convert this mass defect into energy, where we have the formula A equals to mc squared. So this is your mass defect. This is speed of light. This is Einstein famous formula. So this formula is used to convert mass defect to energy. In other words, this is the amount of energy needed to break the nucleus apart into individual nucleons to infinity. Yeah. So, coming back to this question, let's draw a diagram here. Okay. So, okay, wait. we're going to label this as infinity here, because when we want to break this nucleus, we actually break it to its individual nucleons to infinity. Okay, so that is infinity. Now here, I'm going to label this the energy of helium 42. Why I say this is helium-42? Why I did not write deuterium nucleus? Because if you see, the mass defect of helium is actually 0.03, which is greater compared to your deuterium nucleus, which makes sense because what is nuclear fusion? Nuclear fusion when all these three deuterium fuse together to form a more stable nucleus. So this helium is actually a more stable nucleus. The greater the stability of a nucleus, the greater your mass defect. And the greater your mass defect, the greater your energy. Because E equals to mc squared. C is constant. So E is directly proportional to your mass defect. So greater mass defect, that means you need a greater energy to actually break these nucleons apart. Break this nucleus apart to its individual nucleons. Because it's very stable, so it's very hard to break. That's why you need a lot of energy. So the energy needed to break this apart in terms of mass defect is 0.030377 U for helium. So you have a greater energy. Now how about deuterium? So deuterium is probably somewhere here because it has a lesser amount, right? Okay, maybe not exactly half, maybe a bit here. Because it needs a very less energy to break. It needs a very less energy to break the nucleus to its infinity. Nucleus into its individual nucleons towards infinity because it's not very stable. So if it's not very stable, you don't need a lot of energy, right? So if you don't need a lot of energy, less energy means you have a less mass defect. Okay, so this one I'm writing in terms of mass defect. You can then convert this in terms of energy using E equals to mc squared formula. Okay, now going back to what the question wants us to do. They asked to show that the energy released when one nucleus of helium-4 is formed from deuterium. So they want to know what is the energy released when one nucleus of helium-4 is formed from your deuterium. So from deuterium, what is the energy release? So how do we solve this? We take this mass defect minus this. Then, because they're asking of energy, so you take the value after you minus these two and you sub into this formula, you will get your energy release. Okay, so let's do that. But when doing that, you need to be very, very, very careful. Deuterium here, there's 3 in front here. So don't forget to multiply this by 3. Okay, alright. So let's first calculate this difference in mass. What would that be? So that would be 0.030377 minus 3 times by 0.02. Okay, I think there's another one more 0. 0.002388. Okay. U is your atomic mass unit. So you can actually straight away times your atomic mass unit. If you're wondering what is your atomic mass unit, it's actually given in your first page of the formula sheet there. Unified atomic mass unit. It's given here. Yeah, so you don't have to remember. So you can either straight away multiply here 1.66 times 10 to the power of negative 27, or you can multiply later on when you are calculating the energy. So it's up to you. So I'm not going to multiply first. Okay. and this would give me 0.023213 U. As I've always mentioned, in between answer, make sure you have more than 3 significant figures to ensure accuracy. Don't straight away give 2 significant figures, because this is not final answer yet. Okay, and now we're going to use this formula, E equals to mc square, to get your energy release. So 0.023213, because it's U, right? So I'm going to sub in my unified atomic mass unit here, times by 3 times 10 to the power of 8. Don't forget to square. Here you are lucky because they ask you to show this. So you will know if you did not square because you will not get the answer. But if they didn't ask you to show, then you might not know. So always remember to square. And you will get 3.47 times 10 to the power of negative 12 joules. Sure. Yeah. So this drawing here, right, you don't have to draw it in your answer space. You can draw it somewhere else because they will probably not give you mark for this. They will only give you mark for your working. So you can draw it somewhere around the paper so that you can have more space to do your calculations. Okay, now let's move on to question B. A star has a radius of 6.96 times 10 to the power of 8 meters. Okay, helium-4 is produced in this star from deuterium at a mass rate of 7.34 times 10 to the power of 11 kilograms per second. All the energy released from this process is radiated away from the star. All the energy that is radiated from the star is released by this process. Okay. B Roman 1, calculate the luminosity of the star. They want us to find the luminosity. So we know that luminosity is actually power. Am I right? Or in other words, you can also look at the unit here. It's actually in watt, and the unit for power is watt. So what is the formula for power? Power has a formula of energy divided by time. Okay, so we have the value for energy. If you're wondering where is it, it is the value that we actually just found. And why is that so? Because here they said helium-4 is produced in the star from deuterium, right? And that is what we actually found here, from deuterium, and that's the energy, right? So we already have our energy. Now we need to find our time. So given the information they said this helium is produced in the star from deuterium at a mass rate. The mass production rate of helium-4 is actually 7.34 times 10 to the power of 11 kilograms per second. So what can we do to find the time? So to find the number of helium nuclei produced per second, we can actually take, let me write that properly. Okay, we can actually take the mass production rate of helium-4 divided by the mass of one helium nucleus. So this calculation will give us the number of helium-4 nuclei produced per second in the star. The rate of helium-4 nuclei produced in the star. So how do we find the mass of one helium nucleus? We know one helium, what we call atom, the mass of one helium atom is 4U. Mass of one helium atom equals to 4U. Right. So what can we do here is, we take 7.34 times 10 to the power of 11 kilograms per second, divide by 4U, which is mass of one helium atom, right? And how do I know it's 4U? Because they say helium-4. So 4U, 1.66 times 10 to the power of negative 27. So when you calculate this, you will get This is in kg. So if you're wondering why are we using atomic mass unit, like we are multiplying by it, because you want to convert it to kilograms. Okay. So take your calculator. You will get... wait. Okay, thank God. Remember to multiply by 4. You'll get 1.105 times 10 to the power of 38 per second. How I know per second? Because kg cancels out, you will get per second. So what does this value mean? This value gives us the rate of helium-4 nucleus produced per second. So since we have this value now, what we're going to do is we can sub it inside here. So P equals to, our energy was 3.47 times 10 to the power of negative 12. And this is per second already, yeah? So you don't divide by the value. You straight away just times 1.105 times 10 to the power of 38. Yeah, or in other words, okay, let me write it this. E times 1 over T. It's the same thing. So this 1 over T is per second one. So you don't go and divide the value. You just straight away times it. Okay? And you will get your luminosity to be 3.83 times 10 to the power of 26 watt. And that is your final answer. Okay. Yep. Now, moving on to the last question. Use your answer in B Roman 1 to determine the surface temperature of the star. So, to do this, we just have to use a formula, which is luminosity equals to 4 pi sigma r square T4. Is this formula given? Yes, it is given. So, just check if it's given, yeah. Yep, Stephen-Boltzmann law. It's given, so you don't have to memorize it. But usually when you do a lot of questions, because you have the habit of writing the formula, you will somehow remember it. But yeah. So sub in all the value and you would get your answer. 4 pi. This constant is actually 5.67 times 10 to the power of negative 8. This one is actually a very interesting number because you know why? It's 5. This constant value, it's 5, 6, 7, 8. So it's one of the easiest things to remember. Yeah. Your radius is given 6.96 times 10 to the power of 8. Always check your unit, yeah? Always check your unit. Don't underestimate that. Times T4, which is your finding of temperature. So you do your math, you do your calculation, you will get your T to be 5770 Kelvin. And there you go. That is your answer. So yep, so that is all about question 11. The first part is more on nuclear reaction and the energy, and the next part they relate it to luminosity of the star. Yep. So that's all for today's video. I hope you gain a better understanding on nuclear reaction and also luminosity of the star, and how to calculate the time and how do they relate this to the rate of helium nucleus produced per second. It's actually a very interesting one. So I'll see you in the next one. Remember to stay hydrated, and also if you have any questions, don't hesitate to ask me in the comments. I'll always try my best to answer you. Right, bye bye.